We start this lecture with an overview, a plan for what will be presented. We'll first discuss relative motion in one dimension. We will describe this motion in terms of displacement and velocity vectors, which will allow us to generalize our results to 2 and 3 dimensions. We will then discuss reference frames that are accelerating, and will find that the description of phenomena in these frames can be somewhat confusing. For the remainder of the course, we will restrict ourselves to the description of phenomena in inertial reference frames, those frames that are not accelerating. Finally, we will consider a specific motion, namely uniform circular motion, and find that it can be described in terms of a centripetal acceleration that depends on the angular velocity and the radius of the motion. Last time we discovered that two-dimensional projectile motion can be described as a superposition of two one-dimensional motions, namely motion at constant acceleration in the vertical direction and motion at constant velocity in the horizontal direction. We then discussed the description of such a motion from two different reference frames. In particular, we saw that the motion of a ball thrown straight up on a train moving at constant velocity would be described as one-dimensional freefall by an observer on the train, but would be described as a two-dimensional projectile motion by an observer on the ground. Today we will develop a general equation that relates the description of a single motion in different reference frames. We'll start with a one-dimensional case. Suppose you are standing at a train station as a train passes by traveling east at a constant 30 meters per second. Your friend Mike is on the train and is walking toward the back of the train at 1 meter per second in the reference frame of the train. What is Mike's velocity in the reference frame of the station? Intuitively, you probably realize the answer is 29 meters per second, but it's useful to develop, in this one-dimensional example, a procedure that can be easily generalized to the more non-intuitive cases that involve 2 or 3 dimensions. We start by drawing the displacement vectors of Mike in the two reference frames we have here, the train and the ground. At any time, the displacement of Mike with respect to the ground is just equal to the displacement of Mike with respect to the train plus the displacement of the train's origin with respect to the ground's origin. If we now differentiate this equation with respect to time, we obtain the equation we want, an equation that relates the velocities in the two frames. In particular, we see that the velocity of Mike with respect to the ground is equal to the velocity of Mike with respect to the train plus the velocity of the train with respect to the ground. Consequently, if we take east to be positive, then we see that Mike's velocity with respect to the ground is plus 29 meters per second. Had Mike been walking towards the front of the train, his velocity would have been plus 31 meters per second. We now want to consider relative motion in more than one dimension. Here we see Mike in his motorboat crossing a river. The river flows eastward at a speed of 2 meters per second relative to the shore. Mike is heading north relative to the water and moves with a speed of 5 meters per second relative to the water. If you are standing on the shore, how do you describe his motion? How fast is he moving and in what direction? To answer this question, we just apply our equation that relates to velocity vectors, namely, Mike's velocity with respect to the shore is just the vector sum of his velocity with respect to the water, that's 5 meters per second due north, plus the velocity of the river with respect to the shore, that's 2 meters per second due east. Since these velocities are orthogonal, we can evaluate the vector sum using the Pythagorean theorem. Namely, the magnitude of Mike's velocity with respect to the shore is just the length of the hypotenuse of the triangle, which is the square root of 29 meters per second. We can also obtain his direction from this right triangle by noting that tangent of theta is equal to 2/5, where theta is the angle, east of north, that Mike moves as seen by an observer on the shore. This example illustrates all you have to know about relative motion. Writing down the displacement equation and differentiating it yields the relative velocity equation, which can be applied in any relative motion problem. As a note to the curious, though, this derivation does eventually break down once we consider speeds close to the speed of light. Namely, special relativity forces time to be different in these frames, which does invalidate our derivation. More is said on this subject in the text, but for our purposes in this course, we can assume the relative velocities simply add as shown. In the last two slides, we have related observations made in one reference frame with those in another. In both cases, one frame was moving relative to the other with a constant velocity. What would happen if this relative velocity were not constant? In other words, what happens in a reference frame which is accelerating? We'll start with an everyday example. Suppose you have some fuzzy dice hanging from a string tied to the rear view mirror of your car. When you step on the gas and accelerate forward, you see the dice swing backward, just as if something was pushing them toward the back of the car. Indeed, you will feel yourself being pushed back into your seat in exactly the same way. Of course, no one is actually pushing the dice backward, nor is there anything actually pushing you back into the seat either. It just seems that way because you are accelerating. Trying to understand physics in a reference frame that is accelerating can be confusing, since the acceleration itself can easily be mistaken as a push or a pull. For this reason, we usually only consider non-accelerating reference frames in this class, called inertial reference frames. We will develop this framework in the next pre-lecture. For now, though, we will take one more look at this example in order to discuss centripetal acceleration. Suppose you are in the same car discussed in the last slide. Imagine that, instead of accelerating straight ahead, you are now driving with a constant speed, but you're going around a circular track turning to the left. What happens now to the dice suspended from your rear view mirror? Well, they will now swing over to the right. Since there is nothing actually pushing the dice, we conclude that the car, even though it is moving at a constant speed, must be accelerating. We can visualize what's happening here if we consider a bird's eye view and draw in the velocity vector of the moving car as it moves. The direction of this vector is clearly changing as a function of time, even though its magnitude, its speed, remains constant as a function of time. Since the acceleration vector is defined to be the time derivative of the velocity vector, we see that the acceleration of the car is non-zero. The velocity vector changes in time because its direction changes in time. What is the direction and magnitude of the car's acceleration? Well, we can see from the animation that the direction of this change in velocity is a vector that points toward the center of the circle. Since the direction of the acceleration is, by definition, the direction in which the velocity is changing, we see the car's acceleration is towards the center of the circle. This result is consistent with the behavior of the dice hanging from the rear view mirror. Just like before, they are tilted in the opposite direction of the acceleration. What about the magnitude of this acceleration? To determine the magnitude, we have to do some geometry. We'll start by considering two velocity vectors separated in time by a small amount equal to dt. We'll define the angle between these velocity vectors during this time dt to be equal to d theta. We can use the small angle approximation for d theta to obtain the magnitude of dv, the change in velocity vector during the time dt, to be equal to v times d theta. Now the magnitude of the acceleration is just equal to the magnitude of the time rate of change of the velocity, namely dv dt. Therefore, we see that the magnitude of the acceleration is equal to v d theta dt. We will discuss this acceleration and the meaning of d theta dt in more detail on the next slide. We saw on the last slide that an object following a circular path with a constant speed has an acceleration that points toward the center of the circle with a magnitude equal to the speed of the object times the time rate of change of its direction, d theta dt. Since the acceleration vector always points towards the center, we say this motion has centripetal acceleration. It certainly makes sense that the acceleration the car experiences as it turns gets bigger as the speed increases. But what about this d theta dt term? d theta dt, by definition, is equal to the time rate of change of theta, the angle that locates the car with respect to the center. Therefore, d theta dt is a measure of how fast the direction of the car is changing in time, how fast it is turning. Put this way, it does make sense that the acceleration does depend on d theta dt. Imagine driving at the same speed, but turning the steering wheel harder and harder and making your turn tighter. you are turning quicker, so you expect the acceleration to feel bigger. The time rate of change of theta, d theta dt, is called the angular velocity and is usually denoted by the symbol omega. This angular velocity can be determined from the speed v and the radius r that defines a particular uniform circular motion. Namely, the speed is just equal to the distance the car goes in one revolution, the circumference of the circle, divided by the time it takes to make one revolution, the period. Now, the angular velocity is equal to the total angular distance the car travels, 2 pi radians, divided by the time it takes to make one revolution, the period. Comparing these two equations, we see that the angular velocity is just equal to the velocity divided by the radius of the motion. We can now write our expression for the centripetal acceleration in a more familiar way by replacing omega by v over r, or by replacing v by omega r. We'll close by doing a couple of examples to get a feeling for the magnitudes of the accelerations that can be encountered. We'll start by driving around a circular track whose radius is 100 meters. How fast do we have to go in order for the magnitude of our centripetal acceleration to be 1g, the acceleration due to gravity? Setting our expression for the centripetal acceleration equal to 1g, 9.8 meters per second squared, we find that the required velocity is equal to about 31 meters per second, or about 70 miles per hour. You might be interested to know, though, that race car drivers regularly experience even higher accelerations. For example, at the Indianapolis 500, typical accelerations in the turns are about 4 Gs. For our second example, let's consider the rotation of a person at rest on the surface of the Earth. Now, this person, while at rest with respect to the surface of the Earth, is actually moving quite fast with respect to the axis of the Earth. Indeed, this speed is easy to calculate. At the equator, this speed is just equal to the circumference of the Earth divided by the time in one day, which works out to be about 1,000 miles an hour. Now, that's pretty fast, but the quantity of interest here is the centripetal acceleration. When we divide the square of this speed by the radius of the Earth, we find that the acceleration is, in fact, quite small. It's about 1/3 of 1% a g. Now, this value is small enough that we don't really notice it, and we are quite justified in ignoring its effect for any measurements we will make. We can and will assume that the surface of the Earth is a perfectly fine inertial reference frame. By the way, we are also rotating about the Sun once per year. We leave it as an exercise to the student to calculate the centripetal acceleration of this motion. You should find that it is even smaller than that of the rotation of the Earth about its axis. We conclude with a brief discussion of the main points of this pre-lecture. First, we discussed relative motion, how we can relate descriptions of motion as observed in two different reference frames that are moving at constant velocity with respect to each other. From the relation between the displacements in these frames, we obtained the general velocity relations for relative motion, namely that the velocity of A with respect to B is equal to the velocity of A with respect to C plus the velocity of C with respect to B. This expression is totally general when we treat the velocities as vectors. Finally, we examine the case of uniform circular motion in which an object moves in a circle with constant speed. We found that this motion is described by a centripetal acceleration whose direction is always towards the center of the circle and whose magnitude is proportional to the square of the speed divided by the radius of the circle.